All right, guys, so it's Friday, and this will be the second day of La Hopital. I have a district meeting down up in Old Town, so this is the video lecture for today. So remember, Hopital is just another way that you can find limits. We did a whole chapter 1 in Calc 1 on limits, and we did the plugging in, the factoring, multiplying by complex conjugate, looking at sine x over x, a wide variety of different things, getting common denominators. Those are the guys that you had to learn in Calc 1. And there's a new set in Calc 2 that can teach it, can make you do it quicker. But the caveat is it can only be done if it's in one of these 6 forms. So Hopital rule only works if you have one of these 6 forms. And yesterday we really focused on 1 and 2. And today we're going to be looking at 3, 4, 5, and 6. Notice 1 and 2 are fractions and the other 4 are not. And yesterday in my notes I told you it had to be in the fraction form. So today we're going to look at how to change 3, 4, 5, and 6 and make them into the fraction form so we can implement Hopital's rule. This page here might look like chaos to you. You'll see this page again at the end of the notes for today. Oops. But I just wanted to try and color coordinate for you guys the ideas. Yesterday we did 1 and 2, and you should be okay with those. You're going to have some warm up here in a second to practice those. 3, we're going to make a fraction. I'll teach you how to do that today. And then it will look more like 1 and 2. So if you look at x ln of x, if I rewrite that as ln of x over 1 over x, it now will fit into the yellow form that I taught you yesterday. And when you see that 37 and 39 on the side, those are homework problems for tonight. And you can kind of organize and go, oh, that's like the blue style. 4 is going to be the ones that you're the least comfortable with, because you can't just make it a fraction by saying 0 over 0 or infinity over 1. There's an exponent involved, and the only way to bring down an exponent is if you log. Okay, so on these, you have to log it first to pull down that exponent. Once you pull down that exponent, you're going to be able to force a fraction. But remember, your fraction is going to have an ln in it, and you might not be that comfortable with that. So these are the ones that just kind of feel weird to my former students over the last couple years. Those will be problems like 43, 45, cotangent of x. We'll take a look at some of those again today. Then the last one is the purple, which was infinity minus infinity. And you guys are going to be okay with those. The best way to do those is get a common denominator and force it into fraction minus fraction, which then merges into one fraction, and you can handle that. So the yellow you should be good with from yesterday. The blue is the quickest idea of forcing a fraction. Purple, you do a common denominator, and the big one that we're going to have to look at today is how to handle it with logs. This, again, is a page that normally goes at the end of the notes, but since I'm video lecturing, I'm trying to give this to you up front so you can kind of see what our plan is for today. So now, up on the boards, I want you guys to try, I don't know why I have a smiley face here. I want you to try the following 7 problems out: 17, 20, 28, 34, 38, and 42 from the section we're in. So I don't even know what section that is, but on the same page as what your homework was last night. I think 17 was one that was your homework, but I just want you guys to talk through it. And then also this one here that I made up, this limit as x goes to 0. So you can pause the video, go up to the boards, try these out, pace yourself. Once you guys kind of feel okay with it, talking through with your friends, then we can resume the video. Also, I'll have the answer key with the sub today. So if you need to pull up the answer key word for word, not just in the back of the book, but the answer key for evens and odds, you can take a look at that as well. So try these out, go over it with your buddies, and then after that we will resume. Hit and pause. All right, so hopefully you're okay with the 6 from the book, and you tried out this one as well that I made up. I'm going to do the one on the board here, and I'm going to show you the most common mistake that you guys do, okay? Here's what some of you might do. This is a Calc 1 thought. Hey, the degree on top is 2, the degree on bottom's 2, they're equal, so it goes to 3/6, which is 1/2. Because all you're doing is looking at the coefficients in front. Since the degree on top and bottom are the same, 3/6 is leading coefficient, which is 1/2. That's what I taught you in Calc 1. If you did it with Hopital, you guys might have done this. Okay, let me take the derivatives. Derivative on top is 6x plus 1 over, let's see, 12x. That's it. Okay, so then I'm going to do it one more time to get rid of the x's here. So I'm going to get limit as x goes to 0 of 6/12, which is that 1/2. So you guys get it there. And again, you go, woo, 1/2. Both of those are wrong. This would be right. What you just did there would be right. And I bet a lot of you did that. If the limit was the limit as x goes to infinity. Note what I just did there. If x goes to infinity, let's make it a different color here. Oh, that's the same color. Oh, that made it black. Too many highlighters. There we go. Let's do this one. There we go. If it was to infinity, that would be correct. Because remember, when does Hopital work? If it's in an indeterminate form. So when you look at it, if it's to infinity, that would mean I would have, I'll draw in purple here, infinity over infinity, can't do. Indeterminate, so I go again. Infinity over infinity, can go again. 6/12, 1/2. You have it. But was the problem to infinity to start? No, it wasn't. Let me clean it up a little bit so you can see what the real problem officially was. It was not to infinity. It was to 0. So if it's to 0, let me start this whole problem again for you guys. If it's 0, what was the first step you should do? Always plug in. When I plug in here, I get a 1, I get a 4. Is that indeterminate? Nope. Is it a nice number? Yep. Your answer is 1/4. Okay. If you were to graph this guy, what you would have is at 0, there would be a full dot at 0, 1/4. I don't know what everything looks like in the end, but there is an asymptote at 1/2, and there is an asymptote at 1/2. But that's only when you're going to positive infinity and negative infinity. That stuff you could have done with Hopital because it would have been indeterminate forms. But this one, there was no Hopital. You would just plug in. I can do that on the test. I don't want you on this test next Friday to just be thinking, okay, Hopital, 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 boom, 1/2. No. First step, plug in. Make sure it's indeterminate. If it is indeterminate, you can take the derivatives. If it's not indeterminate, you can't do Hopital. And luckily on this one, it's the easiest problem on your test. It's 1/4 and you're done. All right. You guys did those 7. I want to do a couple more with you guys. So I want to look at number 29 from the book. I want to look at this one to see how we can work through this process. Okay, first step, you want to plug in and you want to check and see if it's indeterminate. So if I plug in here, I get infinity over infinity square infinity. So that's indeterminate. So we can do Hopital. So I'll do my next step of Hopital in green here. I get 1 over, okay, 2 square roots of x squared plus 1 with a 2x on top of that. Let me just simplify that. That's 1 over x over this, which is flip and multiply, x squared plus 1 over x. And if I plug in again, limit as x goes to infinity, I get 0 over 0. So that means I can do it again. Stare at that for a second real quick. Look what we started with. We're trying to find the limit of x over that. Now look what we got. It's the same as the limit of the square root over x. Isn't it weird that we took the derivative and it just kind of flipped the top and bottom? The top over the bottom became the bottom over the top, which is still indeterminate, which means I can still do it again. So I'm going to try and do it again. So I'm going to take the derivative of this piece right here. Let's see, I'm going to get 2 square roots of x squared plus 1, the 2x on top, all over the derivative of x, which is 1. That is x over square root of x squared plus 1, which is infinity over infinity again, which means I can do Hopital again. But stare at this guy. I went top over bottom, it flipped to bottom over top, which then flipped back to top over bottom. Do you agree this would be an endless cycle? Oh, cycle. I don't know how to spell cycle. Cycle of x over square root to square root over x to x over square root. Every single one of those would have been infinity over infinity. So every single one of them would have been indeterminate, and you could just keep doing this forever. So we're stuck. It's like, uh-oh, what do we do with this? Well, one thing to ask you is, can you name me a number? And there's only one number in the world that this works with. Can you name me one number where if you flip it upside down, it's the same number? Because apparently I have here, this guy right here, ooh, crayons. That guy has the same limit as the upside down guy. The top guy has the same limit as the other guy, and all I did was flip it upside down. So what number in the world, there's only one, that works with? I'm going to start a new page here for this. Limit x goes to infinity, x over square root x squared plus 1. Okay, and we learned that's the same as the limit as x goes to infinity of the square root of x squared plus 1 over x. So if you tried something, you could be like, okay, if let's say this answer was 1/3, what would it make the other answer? 3 over 1. But we just determined that they're the same. We learned that they were the same, so that one doesn't work. If you try pi, then this would be 1 over pi. That doesn't work. What's the one number that it does work with? What about 1? 1 over 1. Flip it would be 1 over 1. So the only way to get the same number when you flip it upside down is to get the number 1. Now, that's the answer. You could have answered this question way back in Calc 1 if you removed yourself from Hopital. Yeah, Hopital is great, but sometimes you can do it a little bit quicker. This is that whole idea of look at the degree on top and bottom. We talked about this yesterday. So let's go back to this original one here. Degree on top, that's x to the 1. So the top degree equals 1. The bottom degree is not 2. Don't say 2 because it's x squared, but then you square root that. So the key is the square root of x squared makes it still a degree 1. So if that's the case, you look at the leading coefficients. This is 1 in front, and there's a 1 in front there. So what's 1 over the square root of 1? 1. And remember, this only works if you're going to infinity. Okay? Look back at, remind yourself of this one. What was that guy going to? Not infinity. He was going to 0, so you can't do that trick. Okay? Let's just play this out real quick. I don't want you thinking that always goes to 1. If I had a guy like this, let's say 3x over 25x squared, what was it, plus 1? Notice I changed the leading coefficients again. The degree on top is 1, the degree on bottom is 1, so you can look at the leading coefficients. That would be a 3. This is not 25, it's the square root of 25, which is 5. Okay. And if I decided to do it instead of to positive infinity, I did it to negative infinity. Okay, you still have a 3, you still have the 5, but why is there a negative up top? Why did that fraction become negative? Well, you got to remember, you're not plugging in infinity now, you're plugging in negative infinity. When you plug in negative infinity to the top, do you agree you're getting negative 3 big guys? And on bottom, you're getting the square root of 25 big guys. Notice, how come it's not 25 negative big guys? Well, because you're plugging in a negative infinity into x squared. So negative big guys squared equals positive big guys. And then that goes to that. So realize, yes, it's the fraction of the leading coefficients, but be careful on signs. Okay? And I'll do one more for you here. Let's say I go to negative infinity of 3x squared over the square root of 25x to the 4th plus 1. What's the degree on top? 2. Degree on bottom is the square root of x to the 4th, so that means 2. So top and bottom are the same. So I have a 3 and a 5. Now here you might argue it's going to be negative 3/5 because we did that with the red example. But plug in negative infinity. What's negative infinity squared? Positive. What's negative infinity raised to the 4th? Positive. Square root of positive? Positive. So that one would keep it positive 3/5. Okay with that. So that's kind of a rehashing of the Calc 1 notion of looking at the degree on top and bottom. And you can only do that when your limit is going to the extremes, infinity or negative infinity. Okay. Now let's look at 31. This is going to be called the squeeze theorem. We talked about this in Calc 1 very briefly. In this idea, let's see, plug in infinity. I have infinity on bottom, and I don't know what cosine of infinity is. You need to realize cosine of infinity, there's 1, there's negative 1. Cosine of it goes like this. And if you keep going, let's say I'm a little red dot here. Go to infinity, go to infinity, go to infinity. What does this red dot always bounce between? 1 and negative 1. 1 and negative 1. So I have no idea what cosine of infinity is. So it's not one of the 6 original forms. Look at the 6 original forms again. I definitely have the divide by infinity, which is number 2. So I'm hoping the top is infinity as well, but cosine of infinity is not infinity. It doesn't blow up. It bounces between 1 and negative 1. 1 and negative 1. So what you could say is this. Cosine of x over x is going to guarantee be less than 1 over x because the biggest cosine can be is 1. So I'm putting a ceiling. This is my ceiling. And I can also pinch it with a floor. Here's my floor. Because cosine is always greater than negative 1. So I can do this. It's pinched between that. It's squeezed between that. And if you wanted to graph this guy, let's take this version. 1 over x looks like, negative 1 over x looks like this. And let's take this guy. 1 over x looks like this. And all I know about this guy is that he's pinched. Sometimes he will hit the ceiling and the floor, and he bounces up and down, but he's pinched. So, let me ask you this. At infinity, where's the black one go? To 0. At infinity, where's the red one go? 0. And if it holds true, let me hold this down real quick. Sorry about that. Let's see, ungroup. There you go. And if you pull that you know at infinities, the black guy goes to 0, the red guy goes to 0, then I am looking for the limit as x goes to infinity of this guy. Well, the blue guy is forced to be in between the black and the red. If the red pinches and if the black pinches down to the axes, then the blue also has to pinch to the axes. So he goes to 0. That's almost like a logic game. It wasn't the Hopital. You can't necessarily really do the what's the degree on top, what's the degree on bottom, because the degree on bottom is 1. The degree on top, cosine of x, there's no real degree because it's not a polynomial. So you can't really play that game, but you can think through it saying cosine only goes as big as 1 and only goes as small as -1. Black and red both go to 0, so the cosine guy must go to 0. All right, so hopefully that was a good little warm up, the first video, walking you through some examples up on the boards, kind of rehashing what we did yesterday and previewing what we're going to be doing in the next set of videos. All right, so come on in, or stop this video, open up next video.